Good morning and welcome to Argonne National Laboratory's webinar, Frontiers in Materials Manufacturing, Decarbonizing Industry through Electrochemical Processing. Just a few logistical notes before we get started. For a better experience, please check that your VPN is disconnected. Your audio and video were automatically turned off when you joined the webinar. If you have difficulties related to the technology of this webinar, for example, if you can't hear the presenter or see the slides, we recommend you exit and re-enter. The public chat has been disabled. However, we encourage you to remain engaged by asking questions throughout the webinar using the Q&A feature. This feature is the icon labeled Q&A. You can upvote a question by clicking the thumbs up icon. We will respond to as many questions as possible as time allows. Finally, please note that today's webinar is being recorded and will be made available for viewing at a later date. Again, welcome to Argonne's webinar, Frontiers in Materials Manufacturing, Decarbonizing Industry through Electrochemical Processing.
Good morning, everyone, and welcome to Decarbonizing Industry through Electrochemical Processing webinar. I'm Paul Kearns, the Director of Argonne National Laboratory, and I'm very pleased to kick off our 6th webinar as part of Argonne's larger Frontiers and Materials Manufacturing series, which we began about a year ago. This morning, we have an engaging program that will delve into many challenges and opportunities for using cutting-edge technology to drive materials and manufacturing advancements. But first, let me recognize our colleagues from the Department of Energy's Office of Energy Efficiency and Renewable Energy and the Office of Science, along with RPE, for being with us.
Hello, everyone. Thank you.
And give a special thanks to Joe Cresco and Katie Peretti from the Department of Energy's Advanced Manufacturing Office for their participation. And in just a little bit, we will hear from Congressman Bill Foster. You heard him there for a moment. Who represents the 11th Congressional District, which covers the southwest suburbs of Chicago, including the northern part of Argonne's campus in Lamont. Thank you all for being a part of this webinar and for your support of Argonne over the years. Technologies for manufacturing next generation materials are critical to achieving the nation's climate change and decarbonization goals and creating a more vibrant U.S. manufacturing ecosystem that doesn't leave any community behind. Argonne strongly supports DOE's priorities in this important field of science and technology. Much of our work takes place in the recently expanded Materials Engineering Research Facility, or MERF, as we like to call it. At this updated facility, we're collaborating with our industry partners and the DOE to take new approaches to low carbon manufacturing of chemicals and materials. Our scientists and engineers are directly confronting technical roadblocks to move away from fossil fuel-based manufacturing processes. With powerful tools, deep and broad multidisciplinary teams, and state-of-the-art facilities, we are crafting scalable processes for electrochemical manufacturing that can be transitioned for industrial application. Together with our public and private sector partners, we are making great strides at the MERF to support economic growth, job creation, and a robust domestic manufacturing sector that will contribute to a clean energy future. I'm pleased you will have the opportunity later in the program to tour MERF virtually and hope that you will all will be able to have you all on campus soon to see the facility in person. That'd be fantastic. Thank you again for joining today's webinar. I also want to express my appreciation to all the presenters who will be speaking today. They are experts in their fields, and we are grateful for their in-depth involvement and feedback. Together, we will help accelerate the science and technology that will drive U.S. prosperity and security. Now I'm pleased to introduce George Crabtree, Director of the Joint Center for Energy Storage Research. He will moderate today's webinar.
Thank you, Paul. My name is George Crabtree. As Paul said, I'm the Director of the Joint Center for Energy Storage Research, or JCSR, as we like to pronounce it. It's led by Argonne National Laboratory, and I'm also an Argonne Distinguished Fellow. So one of the biggest decarbonization challenges we face is industry, which accounts for about 28% of emissions. Manufacturing, about a quarter of industry, accounts for about 7% of carbon emissions. And it's very important we do not have the commercial technology to address this need. We need to innovate it. One promising opportunity is manufacturing with electrochemistry instead of thermochemistry. Often this can be done at near ambient conditions and with high energy efficiency, unlike thermochemistry, which requires large amounts of high temperature heat and often high pressure. Electrochemical manufacturing has been getting a lot of attention in the last 3 years or so from both the basic science and the industrial communities. And the current emphasis on the need to decarbonize makes exploring this new alternative all the more urgent. So today we have 2 keynote speakers and 2 panels for you. First, Representative Bill Foster, as Paul mentioned, of Illinois' 11th Congressional District, will provide opening remarks. Next, we'll hear from Joe Cresco, Chief Engineer of the Advanced Manufacturing Office at the U.S. Department of Energy. Our second keynote speaker will be Antoine Alenor. He's the Associate Professor of Metallurgy in the Department of Materials Science and Engineering at MIT. Then we'll hear from our first panel, which will discuss the role of industrial electrochemistry in decarbonization, emphasizing the emissions impacts, the business case, and the technology gaps. The second panel will examine the current and future research and development needs in this area. And at that point, we'll hear from Megan Clifford, Argonne's Associate Laboratory Director of Science and Technology Partnerships and Outreach. And finally, and this is a very interesting part of the program, we'll tour some of the facilities at Argonne that are helping companies discover solutions and scale them up in a cost-effective way. First, we'll visit the Electrochemical Discovery Laboratory, where scientists synthesize high-quality materials for electrochemical applications and characterize their properties. Then we'll visit the Continuous Flow Reactor Laboratory at the Materials Engineering Research Facility, or the MERF, as we call it. There, we'll learn how to improve the consistency and efficiency of manufacturing advanced nanostructured materials. Afterwards, we'll visit the Electrodialysis Pilot Plant, where scientists can demonstrate the feasibility of electrochemical processes at scales of hundreds to thousands of gallons. So let's begin with U.S. Representative Bill Foster. Congressman Foster is a scientist and a businessman. He represents the 11th Congressional District of Illinois, position he's held since 2013. He's also represented the 14th Congressional District of Illinois from 2008 to 2011. Remarkably, he's the only PhD physicist in Congress. He also serves on the House Science, Space, and Technology Committee, which addresses some of the country's most pressing issues, including climate change and energy innovation. Because Congress is in session, Representative Foster could not be here live today, but he's provided a pre-recording of his remarks. And Representative Foster, we look forward to what you have to say to us. Thank you so much.
Hello, everyone. Thank you, Paul and/or George, for your usual kind introduction, and for the team at Argonne for inviting me to give remarks today. I'm Congressman Bill Foster. As Congress's PhD physicist, I'm proud to represent Argonne as part of the 11th Congressional District of Illinois in the U.S. House of Representatives. As we know, decarbonization of industry by transitioning thermochemical processes to electrochemical ones will be critical to combating climate change, one of the biggest long-term threats that we face as humans. This April, President Biden committed the United States to cutting greenhouse gas emissions by 50% from 2005 levels by 2030. This is a gargantuan undertaking and will require rapid technological advancements. And the United States has a unique role to play. Although the US has only about 5% of the world's population, we account for over 20% of the world's carbon emissions. So the United States must lead the world, not only in decarbonizing our own economy, but most importantly, by developing low-cost technologies for decarbonization that can be adopted worldwide. The action that we take here and now will serve as a technological and policy template for the rest of the world. And our national labs will be at the forefront of this leadership, facilitating and enhancing the strategic partnerships between industry, government, and academia that will be critical to meeting the necessary decarbonization benchmarks. Since Argonne's inception in the mid-1940s, it's always been at the cutting edge, striving to ensure US prosperity, security, and scientific leadership. Now, Argonne and the other national labs are stepping up to the next challenge, transforming the global economy towards a more efficient and sustainable future. In Congress, we understand your work at the national labs needs support. And as the only PhD physicist in Congress, I understand the value of the work that's conducted at Argonne, and I will continue to fight for federal funding that will sustain and expand this critical pipeline of discovery and innovation. That's one of the reasons I'm the co-sponsor of the Department of Energy's Science for the Future Act, which would continue to support various research and development activities and establish new programming, including basic energy sciences research and development programs. Through continued investment and partnerships, we can start closing the technological gaps that determine scalability and profitability in the thermochemical to electrochemical transition. And today is a big step in the right direction. But you and I know what's really going on here. Electrochemistry is fun. You know, back in the 4th or 5th grade, we started out with, simple school-approved electrolysis experiments with water, baking soda, some wimpy little 9-volt battery to split water to produce hydrogen and oxygen. And we soon realized that AC worked just fine and that we could do much better by just directly connecting this to a wall outlet, as long as we put a light bulb in series to avoid blowing the circuit breaker. And then we realized that we could do much better still by using the giant filament transformer from an old TV, because what you really needed for this was current. This system was able to deliver enough hydrogen and oxygen at enough pressure to fill a medium-sized balloon with an appropriate stoichiometric ratio of hydrogen and oxygen that detonated with a very satisfying thump when you put a match to it. But as George Crabtree mentioned in his video remarks, scale in this is key. So we were eventually able to scale this system to be able to inflate a weather balloon that you could buy for a couple of bucks from Edmund Scientific. And when we released this fully inflated weather balloon, full of hydrogen and oxygen at night with a long wick attached to it, and when it finally detonated at some appropriate altitude, we heard a very satisfying rattle from the windows all around the neighborhood. We later attained another crucial breakthrough when we realized that we could electrolyze salt water to make chlorine and hydrogen, and that could then be recombined in a sort of flame to form fairly concentrated hydrochloric acid, which led to a whole range of new adventures, including some in electroplating. And we even made, at some point, some crude printed circuit boards. It was this sort of entrepreneurial spirit that led my little brother and I, when I was 19 and he was 17, to start a company in our basement with $500 from my parents, a company that now makes most of the computer-controlled theater lighting equipment in the United States and employs over 1,300 people with good pay and good benefits right here in the Midwest. But I must admit that when we started the company, we did benefit greatly from some free nighttime access to the macro assembler on a PDP-5 computer at Oak Ridge National Labs. So to our industry partners here today, take full advantage of the resources that Argonne has to offer. The tools that you have access to here at Argonne offer nearly limitless opportunities and are key to the innovation that will create the technology that will be critical to decarbonization. Again, thank you for having me here today. My only regret is that I can't stay around to see what fun you're going to be up to. I hope you enjoy the rest of today's program.
Thank you, Representative Foster. I really enjoyed your comments about your personal experiences as a boy with electrochemistry. Wonderful to hear that. Now I'd like to introduce Joe Cresco, who is Chief Engineer at U.S. Department of Energy's Advanced Manufacturing Office. He leads efforts at AMO to assess the life cycle and cross-sector impacts of advanced manufacturing technologies. Joe has also served at DOE as an Engineering Sciences Fellow for the Industrial Technologies Program and a Science and Technology Policy Fellow in the Office of Energy Efficiency and Renewable Energy. Joe, we're looking forward to your remarks. The floor is yours.
Great, thank you, George. And let me see if I can share my screen here. I need to quickly get there. Apologies for the delay.
There we go.
And just to confirm, you can see the full screen.
It looks great, Joe. Thanks so much.
All right, well, thank you so much. I'd really like to thank Paul and George for their, and the rest of my colleagues at Argonne for the invite today. It's really an honor to be here, and it really is an honor to follow Bill Foster. I love his comments, and it's just great to really have some memories about high school and college and experiments, whether in the lab or sort of in the garage or the backyard. Today, I really would like to have us think a bit more about the potential and opportunity to decarbonize this very difficult sector, the industrial sector. And the utility of electrochemistry certainly has found its way for a lot of precision applications and precision manufacturing. And we really need to think a bit more broadly about how far can we go with electrochemistry as a pathway for major decarbonization with the industrial sector. So today I really wanted to talk a bit about some of the work we've been doing at the Advanced Manufacturing Office within EERE and within DOE, looking at opportunities for research and development, but also demonstration and deployment of commercially relevant scale decarbonization technologies. And so within today's brief remarks that I'll have, I'll review the industrial decarbonization roadmap that we have under development at DOE. And I'll highlight within there some opportunities for decarbonization that are of particular interest to DOE. These include the direct reduction of metals, the direct synthesis of chemicals, and of course, the use of certain materials that are important. We might be able to have small bursts of energy from setting balloons alight, but hydrogen production is really critical as a potential feedstock as well as fuel for a number of industrial applications. And we can really also think about the full life cycle of materials and how we can think about electrochemical recycling and recovery of materials. So from a high level to kick off today's webinar, I'll try to review some of these elements from a bit of a 30,000 foot scale level. And so as we know, the industrial sector has a really significant energy demand. About a third of the energy demand in this country is attributable to the industrial sector, whether through direct energy use or indirect energy use, the purchase of electricity. And there are a number of ways to reduce that energy demand and the associated emissions footprint. And we'll cover those a bit. Within the roadmap that we've been developing at DOE, we've looked hard at cross-cutting opportunities. And of course, we take a hard look at some of the most energy and emissions intensive sectors. As you can see in the upper right-hand corner, quite a significant amount of our emissions are attributable to the production of cement, food and beverage products, of course, iron and steel, and petroleum refining and chemicals. And so really understanding where the emissions come from and how they're generated today is really critical for us to map out a pathway between now and 2050 to achieve really significant and economical greenhouse gas emissions reductions. So we've done some hard homework within DOE. We've engaged with industry experts, with national lab experts, with academic experts. We were directed by Congress to develop a roadmap. With our engagement with stakeholders and some analysis, we've developed this roadmap that allows us to really take a hard look at what we need to do between now and 2050 to achieve our targets of near zero, essentially, emissions from the industrial sector. And so at a high level, if we take a look at some of these pillars of industrial decarbonization, certainly efficiency is a prime driver, but it's not going to be sufficient for us to achieve deep decarbonization. We need to look at industrial electrification, and we need to look at new, different ways of fueling industry, low carbon fuels and feedstocks and energy sources. And of course, we need to consider carbon capture, utilization, and storage. There's a number of operations that will be truly difficult to decarbonize directly. And if we take a hard look at those and through some scenario analyses, we think we can get to some very, very deep decarbonization within the industrial sector. And when we take a look at what feeds into our scenario analyses, we can really take a hard look at the landscape of research, development, demonstration, and deployment activities that are needed between now and 2050 for these four key pillars: energy efficiency, industrial electrification, low carbon fuels, feedstocks, and energy sources, and carbon capture, utilization, and storage. And between now and 2025 and 2030, we really need to deploy rapidly those high TRL technologies, those at a high technology readiness level, as expeditiously as possible. But concurrently, we need to invest in the research for the next gen of technologies. And when we think about where electrochemistry sort of fits in this picture, we can really begin to think about some very direct applications of electrochemistry. This approaches for metals, for chemicals. And of course, we can begin to think about some indirect approaches. Where research and development is needed, we need to be able to produce the hydrogen that can be used as a reductant, as a fuel for a number of industrial applications. But we also need to be able to do that, develop the electrolyzers and the techniques and the technology, and the approaches at commercially relevant scale to produce hydrogen and other low carbon sources of energy at cost parity or better. And then there's some ancillary issues we have to consider. As we bring on more intermittent and renewable resources, as we need to think about how to include storage, energy storage for the US as well as the industrial sector, and how to scale these, we really need to consider a number of issues that are interrelated and interconnected. None of these opportunities and approaches sort of lives by themselves. So we can take a good look at couple of the examples here. Within iron and steel, we can think and look towards hydrogen direct reduction. Some of the good news is that forms of electrochemistry or electric-based technologies exist out in industry today. For example, electric arc furnaces have been able to drive down the footprint of energy and emissions within the steel making sector for some time now. And we think we can see more expansion there. And it provides a good basis for thinking about scaling opportunities. Direct use of electrolysis, molten oxide electrolysis, may be viable approaches for steel and other metals. And thinking about things like green interactive steelmaking, as we scale these technologies that require significant amounts of energy demand for large scale production, we're really going to need to think about these sort of ancillary and secondary issues. And in chemicals, we can think about new separation processes, catalysts, targeted and precise manufacturing of chemicals, that can lead to sustainable and clean processes. So there's a number of investments that DOE has been making over the years towards industrial decarbonization. Innovative metals processing, we've looked at and are funding work in direct electrolysis, as I've mentioned, in alternative reductants, the hydrogen approaches and others, electrochemical recovery and selective separations, and things like flash iron making is one example of that. We've also really been making investments for some time in very efficient improvements for chemical manufacturing. The Advanced Manufacturing Office has stood up one of the Manufacturing USA Institutes called RAPID that is looking at process intensification and modular chemical processing. And some of the approaches that we've been exploring include one-step electrochemical production of ethylene from CO2. And of course, across outside of AMO and across the department, including our colleagues in the Hydrogen Fuel Cell Technology Office, have been driving towards hydrogen at scale and an energy earth shot called Hydrogen Shot, which seeks to achieve $1 to produce 1 kilogram of clean hydrogen within the next decade. And these types of fundamental transformations, these improvements will lead to significant decarbonization approaches, and even thinking about very cross-cutting approaches that span in different industrial subsectors. Thermal process intensification by developing low thermal budget technologies that utilize low carbon energy sources, such as renewable thermal approaches, are showing significant promise across the industrial sector. And so we can take a hard look within some of these specific sections of the roadmap that's under development, for example, in iron and steel. And it shouldn't be surprising that we can sort of see electrification throughout our roadmap between now and 2050. And again, mimicking what I mentioned earlier, things like molten oxide electrolysis, aqueous electrolysis, or electrowinning. These approaches are examples of our research and development that are needed at scale very soon. And so thinking about showing a couple of examples, decarbonizing iron and steel, direct methods to get there include molten oxide electrolysis. This can produce high quality metal without carbon, removing the blast furnace sort of from the equation of the production of iron and steel. And this can reduce CO2 by 22% with electricity from natural gas, growing by over 90% with the use of clean electricity. And not only can we produce steel this way, but other types of ferroalloys. Additionally, flash iron making is a really intriguing approach to producing iron and steel. Significant CO2 emissions reductions, again, with the use of hydrogen, potentially over 95% emissions reductions. It can save energy, it can intensify the process, and allow for other productivity and competitiveness issues. It will take a significant effort to scale this to full-scale production. Within the chemicals area, again, we're seeing a lot of approaches where hydrogen is an opportunity for decarbonization, separations, developing modular solutions that can allow for more flexible manufacturing. And again, thinking about green integration, how do we do that between now and 2050 so that we can have a fully robust and fully resilient chemical sector, as well as other sectors of the industry. Thinking about some cross-cutting approaches, the thermal demand of the industrial sector is significant. It's well over 7 quads. About 7% of the entire energy demand in this country is attributable to process heating within the industrial sector. Not only is that very large, but a large percentage of that applied energy is lost. More precise heating, more directed utilization of energy is a significant opportunity across all of the industrial sectors. But with that, we need to think about other approaches, because even if we can drive our energy demand down, a lot of the processes we have, including steel and cement, have direct chemical process emissions that need to be addressed. Carbon capture may be an approach for this, and utilization. And within that, there are electrochemistry issues that need to be addressed. So as we've looked at approaches for industrial decarbonization, we recognize that there are some barriers. There's cross-cutting barriers, the scale, the cost, the complexity of supply chains, and just the capital availability of capital to build out a new industrial infrastructure in the US. But with that, we even have very sector-specific barriers. We have very low-cost fossil-based feedstocks today that impact the chemical sector, and cost competitiveness is key for deployment. We have a lot of byproduct interdependencies in the petroleum refining industry. The slate of products that come out is highly precisionally balanced. We can think about market acceptance and regulatory issues as well. And so these approaches technologically will also need to be mirrored with some policy interventions. And so some of the recommendations we have are to pursue decarbonization pillars in parallel. They are interconnected. Invest early in low carbon process technologies, drive capital investment approaches that give multiple benefits and value added and can spur early action. We need to align with the expansion of renewable energy and other low carbon assets. We need to take a portfolio approach and develop a workforce across industries with new skills, diverse skills that can help us accomplish our long-term goals. And so as I begin to wrap this up, I just want to highlight that this is an all of DOE effort. The offices across the Department of Energy have been engaged in a collective and collaborative effort, from the Office of Science to Fossil Energy and Carbon Management to RPE, and our sister offices within EERE, including the Bioenergy Technology Office, the Solar Energy Technology Office. This is an all of the above approach that we need to take to achieve these goals by 2050. And we're up for the challenge. So I'd like to thank you for the ability to make some comments this morning and really look forward to the rest of this workshop. Thank you.
So Joe, thanks so much for that high-level overview. Wonderful for setting the stage. We probably have time for one question, if there is one from the audience. You can use the Q&A feature, and let's see, Aaron, anything out there? But if not, I think we should move on in view of the time. Joe, thanks again for that wonderful high-level overview. You've really set the stage for the webinar. Let's turn now to our second keynote speaker. That's Antoine Alenor. He is Associate Professor of Metallurgy in the Department of Materials Science and Engineering at MIT. After several years of service with ArcelorMittal, sorry, Antoine, if I've mispronounced that, working on greenhouse gas reduction in the steel industry, he teaches metallurgy and conducts research on sustainable metals and minerals processing. Antoine was awarded the TMS Denora Prize in 2012, recognizing outstanding contributions to the reduction of environmental impacts, especially focused on extractive processing. He also received the TMS Early Career Faculty Award in 2015. Antoine had another commitment, unfortunately couldn't be with us live today, but he's provided his keynote in taped remarks. So let's hear what Antoine has to say.
It's a pleasure today to share some insight into how electrification might affect materials and perhaps how using electrochemistry for materials is a way to have synergies around the future. Indeed, the future of materials is heavily focused on electrification, and in a sense, electrification is possible thanks to the list of materials that you see here on the slide. So it starts from structural materials like steel, includes copper and aluminum for conduction, but goes all the way down to silver or rare earth for the magnets and other applications. And you can see that each of these metal or materials come up with large CO2 emissions. And therefore, there's always a question behind more electrification means more material, means more CO2 emissions. So how do we make these things work together? We have to acknowledge that a large fraction of the greenhouse gas emissions and environmental impact in materials come from the sourcing, the supply, and the transformation of the raw materials into a semi-finished product. So my idea today is to share briefly with you how can electrification possibly support the mitigation of the heavy CO2 emission that we can see on this slide. Now, electrification for metal extraction or production is not new. Perhaps the best example is aluminum, which since 1886 is made 100% by electrolysis, so using electricity. You have here a cross-section of an electrochemical reactor, a cell, in which you can find at the bottom the molten aluminum with the gray region with a K here. At the top, some carbon anodes. And then in between, you have an electrolyte, which is denoted here with a T. And this process was invented simultaneously by Martin Hall and Paul Héroux, and relies on that type of chemical reactions where carbon is a fuel. Carbon allows you to reduce the energy needed to make aluminum. But of course, it means that oxygen is going to be combined with carbon to make CO2. And then on the other hand, you have electrons as a reductant, which is allowing you at the cathode to make liquid aluminum. Now, if that story for aluminum is well known and perhaps show a direction for the future, carbon and iron for iron making or steel making have a much longer affair than carbon and aluminum. And probably, thousands of years before Christ, mankind was already able to use carbon, in that time charcoal, to do a very similar chemical reaction where carbon combines with oxygen. But in this situation, carbon is a fuel. It's the thing that allows you to run the reaction and make sure there's enough energy, but it's also the reductant because it directly reacts with the oxygen present in the raw material, in the feedstock. And iron making, which is really the step of going from the iron oxide to iron-rich species, has been done very, very efficiently using coke and coal, as you can see throughout the centuries until the modern age. And there's been a lot of engineering and efforts that have been done, so much that we say that the blast furnace, which is the reactor in which we do this carbon iron oxide reaction, operates near the thermodynamic limits. So there's really not that much opportunities to improve the energy efficiency of iron carbon story. And that's kind of a challenge. Now, we want to also acknowledge that carbon and iron, they have an opportunistic affair when it comes to steel. This is an example of the type of steel products that you will obtain, where you see the mechanical performances evolving depending on the amount of carbon that you add to your iron. So ultimately, thinking about carbon-free steel doesn't make much sense. What we're talking about is really about the reduction. One important aspect about steelmaking in the modern days, in particular for automotive products, is to realize that they are very, very low in carbon, but high in alloying elements. You may know that we use nowadays significant amount of niobium, but also potentially manganese and other alloying elements to get even better performances for lightweight, high structural performances of steel making. So carbon is not going to be moved away from steel soon, but the question would be, how about using electricity? Now, electricity and steel making have also a long-standing history with the example of the electric arc furnace. It happens that Héroux, which you see here on the left, invented also the electric arc furnace, and that's what allows us today to use recycled materials and recycle more steel products. This is showing you the energy consumption per ton of steel in the USA in the last 40 years. And you can see that there's been a significant reduction in energy consumption. And that's because we've been using more recycled products in an electric arc furnace operation mostly. And if you think about electric arc furnace, you will also realize that ferroalloys and many other iron-based systems are able to be made in an electric arc furnace. But the electric arc furnace uses both carbon and electricity. Now, if we know about the performance of electric arc furnace for steel making, you may wonder, how about iron making? And here is a quote from a book written in 1901 by a very famous author, Émile Zola, who's describing an owner of an iron and steel making plant, Mr. Smelt, who was threatened. In this book, Zola explains that that owner was aware of the researches made by someone, which I named Coulon here, which wanted to replace the old, slow, barbarous smeltery by batteries of electrical furnaces. So this is 1901, and you can see that a very popular writer describes already how electricity could completely change the way we make steel. But you can see the last sentence here that says that at the time in 1901, the price of electricity was such that, you know, it would be a futility to replace the blast furnace or carbon-based processes with electrochemistry. And of course, at that time, Émile Zola relates what Héroult was doing, both for aluminum electrowinning and electrolysis, as well as the electric arc furnace. Now, you step forward probably almost 100 years after, in very early 2000s, there's been several initiatives to think about how to reduce CO2 emission from steelmaking. And you may remember this plot that shows you all the options that are possible. And clearly electrons and electrolysis is one of the way forward that was investigated as early as 2004, both with the DOE AISI as well as the European Union. And in there you will find that really iron making is about making an iron-rich product from an oxygen-rich product. And of course, steel and iron will be made from the bottom red spheres here, but it's a separation problem. And a separation problem can be very well addressed using electricity and electrolysis, as we know from our basics knowledge of chemistry. Can we do that at scale? I already mentioned. Aluminum is made at more than 60 million tons per year through those cells that I'm showing you here. This is a capacity of almost 600,000 tons per year for one plant. So we can scale and think about large-scale electrolysis without problem. But of course, we need to be aware of these two parameters that I'm bringing up here, the operating cost and the capital cost. Now, there's a lot of engineering that goes behind those two numbers. Some of them relate to the cell voltage, basically the voltage cost of doing the reaction, but also the current efficiency or current density, as well as the materials that you're going to use to build those reactors. And here we've been able to show, for example, if you rank the different electrolysis technology, if you rank them as a function of temperature, you see some interesting trend, which some of the conclusions are written here. Your capital expenditure, so the capital cost of building a greenfield electrowinning operation is not just related to current density or low temperature. You could think of going to very high temperature, in which case you have such a high productivity, which is represented here by the right axis in current density. You have such a high current density that your capex actually per ton of metal and square meter is going down pretty drastically. And there is this middle ground where you're not hot enough to use very cheap refractory material, but also not hot enough to have very high current density, where it's very questionable if there's going to be an opening in that temperature range. Now, something that is not presented on that graph is the fact that, of course, you need front-end treatment of what you're going to feed your electrowinning reactor with, and that can be very significant. This is also mentioned in that article. It can be up to 50% of the overall capex is going to be deployed in order to prepare the raw materials for electrowinning or to handle the product of electrolysis. Now, when it comes to iron chemistry, there are many challenges that explain why, in addition to the cost challenge of steel, there's been a slow development of iron electrowinning. But here are two examples that are very active today. The first one is at low temperature. It's called alkaline electrowinning. It's done in a sodium hydroxide solution at not very high temperature. And here you can find that you can make solid plates of iron, which can be up to a centimeter thickness. Dimensions have to be pretty easy to decide. And the Faradic efficiency and the energy efficiency are quite high in those conditions. And that process is under development currently in the European Union in the project Cedar Wind. If you go on the opposite side of the chart that I showed before, you go to very high temperature, in which case you can potentially make liquid metal, liquid iron, which means the temperature is greater than 1535 degrees Celsius. And one of the processes that has been put forward is called molten oxide electrolysis, where one of the challenge was to find an inert anode material to evolve oxygen at the positive end of the electrochemical reactor. Now, there are various features that are under development now, including very good heat management, because the temperature is quite high, and you want good heat management to make sure you have high energy efficiency and you can decrease the cost of using electrons for those processes. Now, if I may, I would like to open up the discussion further than this pretty old problem. You may have seen that this dates from 1990, 2000s, because in our lab, we are, for example, looking at very different type of chemistry. One of the examples is the sulfide chemistry, where you could think of a molten sulfide electrolyte, which will allow you to evolve elemental sulfur on one electrode and make a metal at the bottom, potentially liquid, of the reactor. Now, the reason why you would move to molten sulfide electrolyte is because you have a high solubility of sulfides. Sulfides have a high conductivity. They are a very impressive chemical medium to dissolve and bind with any feedstock, and therefore we anticipate we can have high conductivity and high current density. One of the examples of this development happened with the support of the US DOE EERE office, where we investigated the processing of a natural mineral concentrate, which is called chalcopyrite, which, if you look at the chemical formula, tells you is made 1/3 of copper, 1/3 of iron, and 1/3 of sulfur. And what we're trying to do is to do the selective decomposition solely with electricity of the chalcopyrite. In the tiny movie that is shown here, you get an idea of how this would look like. You imagine a concentrate that's coming in, which contains copper, iron, and sulfur. The sulfur are the yellow or green spheres which are coming out at the anode, which is the positive electrode. And then in the first step, you remove the iron from the system, and therefore you can have a liquid cast iron product or iron product. And then on the second step, once you have depleted enough in iron, you can sequentially recover the copper as the second valuable metal. In this system, there is no oxygen, and therefore any of the valuable elements that come with copper, iron, sulfide will be recovered as elemental species, either metallic species or, as you can see, anodic gas, which you can condensate and get as a solid product. We have been able to develop the entire sequence of processing necessary from the ore or mineral all the way down to the two metal products. The first step that we are developing, as you can see at the kilogram scale, is called sulfidation. The sulfidation is here to make sure that everything forms a sulfide. And once you have a sulfide, you can feed in the second operation that you're seeing here, which is the electrowinning electrolysis reactor, where you have an idea of the scale of that operation currently. Now, in this operation, we've been able to successively produce iron. You can see the droplet of liquid iron, which are about 1 centimeter cube, that are found on the first step. And then we have been able to produce copper, which you can see here on the right as the second step of the process. The cell technology is the same. It's just the operating conditions and parameter are slightly different depending if you're making the iron step or the copper step. With this, I think I've shown you a different way electrification is going to be tied to material, and most probably we would have to do more electrochemistry, more electrochemical engineering in order to decrease the CO2 emission from materials production and support and allow electrification. So with this, I really appreciated the opportunity to share this material with you, and I wish you a very entertaining webinar.
So thanks so much, Antoine. What a wonderful perspective, how we got here with iron, steel, and aluminum, and where we might go to decarbonize. Those options you presented are really, really fascinating. Next is our first panel, which will explore the role of electrochemistry in industrial decarbonization. It will be moderated by Jeff Spangenberger, who is the group leader for materials recycling and the director of DOE's Resell Center, which is a national collaboration of industry, academia, and national laboratories working together to advance battery recycling technologies. The center has its headquarters here at Argonne. Jeff, maybe you can introduce the panel, and we look forward to what you guys are going to tell us. Take it away.
Thank you, George. And thank you all for joining us today. I'd like to invite the panelists to share their video, and we can all, I think, be up on the stage at the same time, if that's okay with everybody. In this first panel, we'll hear from experts regarding the role of electrochemistry in industrial carbonization. Using electrochemistry for decarbonization means pretty big changes to how industry produces products, and that makes people a little nervous. But it reminds me of the switch to LED light bulbs in our houses. The switch needed to be made. After all, the light from a 60-watt incandescent bulb can be made with an LED bulb that uses only 8 watts. And that's about 15% of the energy consumption. Now, at the time of the switch, I was concerned about the quality of light, the color of the light, and most importantly, the cost of the new bulbs. Now, there may have been some bumps in the road, but I'll fast forward to today. And I have to say that I don't even really think about it anymore. The quality of the light, the color of the light are all great, and the price is about the same as what an incandescent bulb would be today. Now, zoom out and consider what we've done as a result of taking that challenge on. Our household electricity bills have gone down, and the country has reduced its electricity needs by an enormous amount as a result of this. And I think about this and ask, was it worth it? And I easily say yes. This similar type of opportunity with using electrochemistry to decarbonize the industry with even more potential for benefit is presented to us today. We have some experts here with us now to talk about this opportunity, so let's get started. Let's see, first let me quickly introduce you just with some words that I have, and then I'm going to let them speak a little bit on their own. But Wei Kai is the Director of Energy Transformation Technology and Inclusion and Diversity Leader. Throughout her career at GE, she has led technology development at different phases, ranging from ideas discovery to feasibility validation, prototype building, and all the way to new product introduction. Runil Dalia is a senior analyst at Lux Research. He currently leads the group's coverage on the decarbonization of energy system, focusing on carbon capture and utilization and the hydrogen economy. And Ping Sun, who is a principal energy systems analyst here at Argonne. She works on energy systems analysis and technology evaluation by techno-economic analysis and life cycle analysis. Thank you all for participating in this panel discussion. I really do appreciate it. I'd like to let each of you say a bit about yourselves before we get into the Q&A. So Wei, can we start with you? And I think there's a slide.
Yes, thank you, Jeff. I really appreciate and also feel honored to be joining this panel, this group of experts to tell you about my opinion about how electrochemistry and overall how we can contribute or together to solve the decarbonization grand challenge. So quickly, I mean, Jeff kind of told you where I was, and so my passion with electrochemistry actually started in graduate school. So I studied impedance spectroscopy in my graduate school. Then the product, one thing really interesting that I personally made it real was electrochemical separation, which is part of desalination. Back when GE still have a water business, we developed a new lower cost and high efficiency device that removes salt from water, which is also fouling resistant. So that's kind of where I was, but now I think when we move into this decarbonization phase, in our company, GE Research, we really look into ways how we deploy the decarbonized power gen, right? Because GE generated a third of world's electricity. How we do that lower carbon, whether it's carbon sequestration, renewables, or hydrogen, using hydrogen to as a fuel. And then the second is really develop the carbon capture, because we need that for all our installed base. And then the third is sustainable aviation fuel, which is really important and relevant to this electrochemistry community, because we know that co-electrolysis or electrolysis is a way to make hydrogen and possibly make hydrocarbons for the future of aviation. So I think this forum is so important for industries and academia and also a collaborator coming together on that we exchange ideas and really move this forward. We will talk more at the panel. Turn it over back to you, Jeff.
All right, thank you, Wei. Let's turn to Renil. Renil, can you tell us a bit more about yourself?
Yes, of course, and thank you very much, Jeff. So hello, everyone. It's a pleasure to be here with you today. Thanks to Argonne for inviting me to participate in the panel today. So I really appreciate the opportunity. As Jeff mentioned, my name is Renil Delia. I am based in Amsterdam, in the Netherlands. So I am from Lux Research. For those of you who are unfamiliar with Lux and what we do, we're an advisory firm where our focus is on technology innovations for various sectors, including energy, materials, and the agri-food sector. So our job is really to scout the global innovation landscape and identify the key technologies and companies that are developing these technologies. So identify these companies that will impact the future of the industrial sector. And we work directly with companies, large corporations in the energy, chemicals, and materials space. So as for myself, as Jeff mentioned, I lead our coverage on the decarbonization of the energy system. So as part of my role, my job is to identify which technologies will be required for us to reach net zero emissions, but also how will these technologies evolve, both in terms of the development of these technologies as well as the deployment. Now, electrochemistry is one such technology. And over the past years, we've put in a lot of efforts into assessing electrochemical technologies such as water electrolysis and CO2 electrolysis, talking with the various companies and technology developers around the world, but also speaking with players in the industrial sector that are interested in adopting these electrochemical technologies in their portfolio as they decarbonize their operation. So I'm very happy to share these insights with you here today.
Thanks, Renil. And Ping Ping, how about you?
Thanks, Jeff. Good morning, everyone. It is my great pleasure to join this panel. So as Jeff introduced, I'm Ping Ping San. I work in Systems Assessment Center, or SAC, of Argonne. So on the right corner, you can see great model. Our center works on a lot of PA and LC analysis. And our so great model, as many of you have known, it is our core software, our core scale to do life cycle analysis. So in terms of my work scope, my background is chemical engineering, and my work includes both technical economic analysis and life cycle analysis. So our work scope includes the CO2 capture and utilization, especially CO2 utilization for fuels and chemicals, and the industry sector decarbonization, closely related to today's topic. For example, as many of you have mentioned, steel sector decarbonization and ammonia sector decarbonization, as well as the refinery and the petrochemical sector and others. So especially we observed upon our analysis of various industry sectors that hydrogen plays a very essential role in decarbonization. Especially hydrogen needs to be produced from electrochemical pathway by electrolysis by using clean energy. So we can discuss more about it. In addition, our center also do fuels analysis for the transportation sector and also waste conversion, such as plastic waste, for fuels and chemicals. So about myself, as mentioned, my background is chemical engineering, and prior to joining Argonne, I also worked in industry, oil refinery industry for technology development. So all these past experience allow me to do my analysis with more in-depth understanding and also with the consideration of engineering practice. Thank you.
All right. Thanks, Ping Ping. Now let's get into some questions. I'd also like to remind everybody in the audience to type in your questions in the Q&A. That will help in the discussion greatly. I'd like to know what everybody out there is really curious about. But let me start with Runil. Runil, what's the current state of industrial electrochemistry as a lever for reducing emissions? And how attractive is this opportunity from a business standpoint?
Yeah, thank you, Jeff. So I think when it comes to electrochemistry, it's important to distinguish between the various electrochemical technologies that the industry is currently looking at today. So we've seen some of them earlier in the presentations, but among these emerging options, water electrolysis is of course by far the most popular one, where you're making hydrogen from water and electricity. Currently, this is a technology that is being scaled up at quite a rapid pace in industry today. So today we already have electrolyzers in the range of 10 to 20 megawatt, but we're already seeing gigawatt scale projects being announced for later this decade all over the world. But water electrolysis is not the only platform being looked at the moment. If you take the chemical industry in particular, they are quite interested in CO2 electrolysis, where you're using electricity to make carbon monoxide or methanol or ethylene from CO2 in a single step. So what these two platforms have in common, of course, is that you're using electricity to drive forward the conversion process. And this is why it becomes interesting from a business standpoint. So with electrochemistry, we don't need fossil fuels such as coal or natural gas. And if the electricity that you're using is renewable, you essentially decarbonize your operations. Now, of course, decarbonization is the goal with implementing electrochemistry, but another advantage that you have is that you also decouple yourself from the oil and gas industry. And this is very important for the chemical industry, because with electrochemistry, the chemical industry also has the opportunity to secure their own feedstock, which means that they have greater control over their supply chain. So this is what makes it very interesting for the industrial sector, not just decarbonization, but also about securing your supply chain.
Great, great. Thanks, Runil. I'd like to offer Wei or Ping Ping. Do you have anything to add to that? I'm particularly interested in the opportunity for business standpoint too. I think that's a really good thing to dive further into.
Yeah, I think from our assessing, current state as we saw it from 2 years ago, the rapid ramp up of the electrolysis technology. The one thing bottleneck is how you automate that, right? And also the overall cost reduction. People were thinking, okay, costs will come down, like we saw in the solar panels, those will go over. But overall, where's the cost? Electricity cost is 50% of electrolysis process. So electricity costs have to come down as well. And so the renewables have to scale up. So those are linked. So electricity costs, where is the cheapest electricity? Solar in Middle East or and then 24/7. Electrolyzer is a piece of equipment. You want to get the most out of it in the way you want to operate 24/7, right? 24/7 meaning you need to have the renewable electricity all the time. So where is it? If you're using renewable energy, so then energy storage comes to play, right? Because the sun is not always shining, but there is sun shining somewhere on the earth. So hydro, so I think we need to put these things into broader context because electricity costs today is still the majority of the electrolysis. But I mean, efficiency can go up, and PEM and SOEC, there is a theoretical bottleneck of the efficiency. Those material scientists, I trust you will discover new material more efficient, but still, as we see it, is integration, system level play, because there are also converters, inverters, right? How you ramp up and down with the rest of the grid. If it's not solely dedicated solar or wind for the electrolyzer. So those are much larger scale questions to consider. So there is not only electrochemists to play, but also controls, electrical engineers. We have to work together to look at how to optimize electrolyzer, make the overall cost of production of hydrogen low.
Thanks, Wei. Ping, no pressure, but anything to add?
Oh yeah, I totally agree with Ranil and Wei. You know, it really requires a system integration. So electricity cost, it is really key for decarbonization of many sectors. But then when we think about the cheap renewable electricity, the energy storage becomes like important. That is your expertise, Jeff.
Okay, great. Great. Let's move on to another question, if that's okay. I see questions coming in actually in the question and answer or the Q&A, and I'm anxious to get to those. So I'm going to try and maybe pick this up a little bit. Ping, what sectors or products stand to benefit the most from innovations in industrial electrochemistry, both from an emissions standpoint and profitability standpoint?
Thank you, Jeff. That is really a big topic, and it is hard to pick up a champion without actually doing analysis for every single sector. But I would say generally, you know, with the green hydrogen application, many sectors can benefit from it. When we talk about the electrochemistry application, in our opinion, we can think about in two ways. So first will be the direct application of electrochemical, application, such as the chloroalkaline industry. They use electrolysis, such as water split, you produce hydrogen. And such as, iron making or metal reduction, such as copper reduction, nickel reduction, just as Antonio mentioned in his presentation. So those are the direct application of electrochemistry. And so therefore, this industry needs a direct application of the electrochemistry can really impact these factors significantly by using renewable electricity. And on the other side, there's the indirect application of electrochemistry, namely the green hydrogen production. That can have a broad impact across all the sectors. Because you can think about hydrogen has basically two functions. First, it is a really good reducing agent. It can be applied to iron making, industry, for example. Also, the second one, it is also a good energy carrier. And it has zero carbon emission if it is produced from electrolysis by using clean electricity. So therefore, if you can use hydrogen to replace heating sources such as fossil or petroleum energy sources, then any industry sector that uses heat by using with the field combustion to supply heat and steam can benefit from green hydrogen application. with the knowledge of electrochemistry. So for example, for iron and steel sector, it will be, currently a lot of emission is caused by the unit or the process of BF, which uses coal as both fuel and the feedstock. It will be switched, coal to hydrogen by using the new technology of DRI. Then the on-site emission can be reduced by 80 or 90%. And another example would be ammonia plant. So right now, in ammonia plant, hydrogen is produced from steam methane reforming by using natural gas, which is used as both feedstock and fuel. If we place this hydrogen produced from SMR to electrolysis hydrogen by using clean electricity, the on-site emission can be reduced to 0. So those are the examples of sectors that can really benefit from electrochemistry directly and indirectly. And in terms of cost, we would say, based on our current analysis or knowledge, a lot of sectors that using green hydrogen based on current technology would cost the premium of production cost. So for example, for green ammonia, if you base on current hydrogen cost of $5 per kilogram by electrolysis, then ammonia cost will be $1,000 per metric ton. It's much higher than the current market price of $300 or $400 per metric ton. However, if we can reach the DOE long-term target from hydrogen office, HFTO office of $1 per kilogram of hydrogen, and all these processes by using green hydrogen will become profitable, or at least comparable with current technology.
Okay, thanks, Peng Peng. Appreciate that. Wei, what are the key technology gaps that we face?
Yeah, there are a lot of them, but I will pick a couple of them relevant here. So we already talked about hydrogen, right? So I think productions at scale, that's because it's a huge challenge. If you think about if you want to supply hydrogen for gas turbine, how the rate of the run, how much of electrolyzer, it's going to be covered everywhere. So that's the thing, like our industry partner or our business is scratching their head. Our gas turbine can burn hydrogen today, but where is that hydrogen? We install a gas turbine at the customer site and for them to be future ready, but they are waiting for the hydrogen to come through the pipelines. So can we generate on site? I don't know how fast kinetics, chemistry does that. I think the flow rate it cannot do that today. So that's one thing. The other is if we generate somewhere, how you transport it. Storage, transportation, those are all different challenges. So that's about hydrogen. Then talk about another electrolysis, which is very promising for fuel production, for chemical synthesis. I think it's in the future, think about there is no fossil fuel, for example, for aviation, because GE has a pretty significant footprint in aviation industry. So we are really working with airlines and the industry to look at ways how to using carbon neutral fuels in the future. So people are using biofuels, but biofuels are constrained by land, by biomass availability. The other way to make it using co-electrolysis or electrolysis, right? You take water and CO2, or you make hydrocarbons in the end. Although right now it's not all the way, you can make intermediates like methanol or syngas and go to the hydrocarbons. But the challenge there is it's nascent. It's still early stage development. We need good chemical catalysis material, make that happen in a high efficiency. And we need device that can integrate, that can easy to manufacture and easy to scale up. For example, SOEC type of kind of electrolysis, right? Material is always a challenge. Then durability. How durable, how long it can operate. Those are a lot of challenges that I hope DOE, I know DOE is wanted to invest in these directions. I think given the world, if we assume we have abundant electricity in the future, electricity cost is not an issue anymore. I think with the technology, with the advancement in materials, component manufacturing, we will make kind of clean carbon neutral fuels out of water and the CO2. That's my kind of call to action. Here's a gap. Let's work on it.
I like it. There's a question I can't help avoid asking that's in the Q&A. And so let me ask this question. Water hydrolysis to produce hydrogen is dependent upon iridium-based catalysts. Iridium is a limiting component for this process. And what advances are being done in this area? Is that, in a way, I'll give it to you, but if anybody else has anything they'd like to tackle that with.
I think there are, I think we are working on the, like we worked on fuel cell in the past, which is applicable to electrolysis too. I think if you look at, we worked on the SOEC side of the high temperature electrolysis, which we can avoid using that material. So I think there are ways, there are universities, a lot of academia, and we can using low cost ceramic materials as a catalyst. I think PEM, they have been reducing using of the platinum material in the past 10 or 15 years. I think there are a lot of alternative ways to do that.
I think perhaps I can add on to that. I'm very glad that this question was asked actually, because with the discussions that we're having with people in industry, the issue of iridium is not something that is being looked at deep enough, in my opinion. Now, there was a study from Voltechem, the European institute that's developing electrochemistry in Europe, and they found out that in a high hydrogen demand scenario, Europe alone will need 110% of the world's annual production of iridium just for electrolysis. And that's just for Europe. It's not even considering other regions like the US, Australia, or South America that are also looking to produce a lot of green hydrogen, presumably from a PEM electrolyzer. So that's definitely something that needs to be tackled very soon, because we don't have enough iridium to meet our ambitions for green hydrogen. Now, I don't know what advances are being made specifically in iridium, but there is an emerging electrolyzer technology called the anionic exchange membrane electrolyzer, which is a membrane electrolyzer that does not use iridium metal. It uses a nickel electrocatalyst. So it has a similar performance to a PM electrolyzer, but the membrane is different and it does not use precious metals. That's one technology innovation that is circumventing the use of iridium in electrolysis.
Good, thanks. This is a question along the same lines as what we've been talking about with technology gaps, and this is open to anybody. Where should we focus resources on innovation?
Maybe I can go first for this one, because Wei brought up a good point earlier around the contribution of electricity to the total cost of production of these chemicals from the electrolysis. Now, it's well established now that when it comes to making hydrogen, but also when it comes to making carbon monoxide and ethylene, for example, from the CO2 electrolyzer, the use of electricity is by far the largest contributor to the total cost of production. Now, the price of renewable electricity around the world is falling quite rapidly, which means that now is the good time to scale up these electrochemical technologies. And this is where improvements can still be made around the scale up of the manufacturing for these electrolyzer cell components. Now, there is potential, quite a large potential, for a system cost reduction with a scale up of the manufacturing supply chain. So with technologies like automation and so on, you will get quite a reduction in system costs. So this is an area, I think, where innovation can really have an impact, identifying the best tools and resources to optimize the large scale manufacturing of these electrolyzer components.
So from where I
will-
sit,
Okay,
sorry, go ahead. Go ahead.
okay, go ahead. Right. Okay, thank you. So yeah, I would like to share some thoughts. As Joe mentioned in his presentation, which I totally agree that the efforts have to be made from all aspects. So for example, when we talk about low cost, renewable electricity from solar, wind, then we talk about the energy storage. And when we talk about green hydrogen application, we need to talk about the transportation and storage. From current SMR, hydrogen is produced with $1.5 per kilogram, but the transportation of hydrogen costs $6 to $8 per kilogram. It's certainly a lot of room and a lot of urgency to improve in this cost by reducing the cost. And from, just as we mentioned, to improve the electrolysis, efficiency from like a water split. So that requires the, effort from anode material, cathode material development in terms of catalysis, material synthesis, and, membrane development. And also engineering configuration. So all these factors contribute to the cost reduction of the new material and new energy source, and also decarbonization. So I guess this is a broad that efforts, just as Joe listed in the presentation, effort from all aspects are really needed, and it is kind of urgent to conduct this concerted effort to decarbonize the industry sector.
And one thing I want to add from where I sit, right, we were right now, our hybrid business or renewable business already, we wanted to deploy or integrate electrolyzers with our renewable electrons. But overall, the market, everything seems like it's taking off, but the pricing is not there yet. So I would say for hydrogen, or in order to scale up electrolysis, we need policy support and also some of the incentives to nurture those demonstration projects in a larger scale in US. We saw that in Europe happening, not only for the hydrogen production, but also for fuel, for hydrocarbon production. Those kind of demo will give people confidence of how you scale 10 times, 100 times, or 1,000 times larger than from a lab or from a prototype. So I think that's really we need to focus on the partnership between private sector and the government, and also national labs and academia to really cross that chasm, right, where most of the technology will fail at the where we're going up to scale up. So that's where I think as a country we need to put more dollars or investment over there.
Okay, thanks for all your answers. That's good. That's great. All right, so suppose it's 2030 and we've succeeded in reducing industrial emissions and are on track with the administration's goals towards 2050. Industrial electrochemistry has been an important part of the solution. What did we have to do to get here? And in addition to developing technologies? Any thoughts on that? That's a tough one.
I think, yeah. Where do you want to go first?
Yeah, let me take crack, because we cover a lot, right? We cover the policy, technology, but one thing we haven't covered is the workforce readiness, right? Do we have enough of electrochemists, or do we have enough of material scientists? Because material science is really the key, because a lot of catalysts, new catalysts, cheaper, high efficiency need to be developed. So really the whole kind of education, workforce readiness that need to be happening. In addition to technology, where the idea comes from our brains, right? Who's the next generation? That's what I will start with.
Yeah, I would agree with Wei as well here. And this is especially important when it comes to commercialization, because what we're seeing now is that you see large oil and gas companies and chemical companies are looking to deploy electrochemistry in their operations. Now, these companies, they've been reliant on thermochemistry for the past decades or century, depending on how old they are. And for them to transition to a new way of making things is not easy. So they really need to beef up their workforce in electrochemistry. So it's definitely one area that needs to be looked at if you want to get to net zero by 2050 with electrochemistry. The other thing that we need, I would say, is really regulatory support. And that's in the form of incentives for low carbon products. Because at the end of the day, whether you're making a chemical from electrolysis or a steel product using hydrogen that was derived from electricity, it's very likely that that product is going to be more expensive than if you had made it with fossil fuel. And that's unfortunately just the way it is, because the oil and gas sector, they had decades to optimize and bring the costs down, whereas for electrochemistry, we don't really have decades because we need to get to net zero by 2050. So it's very hard to convince a large oil and gas or a chemical player to adopt a low carbon technology like electrolysis, if that means that their product will now be more expensive than that of their competitor who are still using fossil fuel. Now, for example, we saw a presentation from ArcelorMittal earlier, but there's also Saab, the Swedish steelmaker, that is developing a technology that uses green hydrogen in a direct reduced iron process for steelmaking. And they publicly said that using that hydrogen will make their steel product 30% more expensive than if they made it from coal, which means that for them to succeed, you really need to have these regulatory systems in place that will either penalize the use of fossil fuel or give credits that will offset the premium on that green steel. So regulatory support is very important for us to reach that net zero by 2050 with electrification.
I would like to share my 2 cents as well. So I agree with Wei and Renu, and I think, I can think of from like three aspects. So the first one, as everyone just mentioned, money talks. So for the broader adoption of electrochemistry, overall industry have to adopt this new technology or the new process. And what drives them to do that would be economics. So technology development would be really needed to help them to adopt. And then meanwhile, policy support, that's my second point, is a policy, continuous and consistent and policy support, either by tax credit or by, I wouldn't say penalty, but I would say this encouragement of continuous utilization of fossil fuels. So these will really incentivize industry partners to adopt cleaner, decarbonization technologies. And the third point I would say would be public pressure or public support. In recent years, we have seen that, the public awareness of climate change and also decarbonization incentive really help, them to push industry to switch to cleaner energy, such as from stakeholder meetings for major oil companies, and the stakeholders will really pressure them to switch to cleaner energy. And we observe that it works. So I would say all these 3 elements would contribute to the switch. And of course, probably there are a lot more other factors.
Very good, Ping Ping. Thank you for that. And thank you to all 3 of you. I think we're running out of time. And I didn't even get to all the questions that I wanted to ask. And there's also questions in the chat. I would encourage folks, if you have any more questions for us, to go ahead and put them in not in the chat, but in the Q&A, and the panelists can have an opportunity to answer those. So again, thank you very much for your time today, and all the insightful information that you have provided. And I think we're going to send it back to George now.
Great, thanks so much, Jeff. Really appreciate the panel's contributions. It gave me a much better insight as to what some of the problems are, namely getting the price of electricity down, which is going to be important across the whole industrial landscape. Also, creating more electrochemists, and finally, just policy. It's very different when you have a time limit of 2050 to decarbonize, and the other transitions that we've seen up until now haven't had that sense of urgency. So thanks so much. Let's turn now to the second panel and dive into the current and emerging R&D that needs to be done in order to decarbonize by 2050. John Hearn will moderate the second panel. He leads the Emergent Materials and Processes group, and he's an expert in aluminum and magnesium processing and recycling and electrodialysis processing. So John, if you would introduce the panelists, the floor is yours. Thank you.
Thank you, George. So good morning, everybody, or good day, wherever you are today. I would like to say that when I started in this field back at MIT, I caught the bug. I caught the electrification bug and the decarbonization bug. And both of these things came about from my interaction as a postdoc at MIT, where we actually talked about inert anodes for aluminum production and molten oxide electrolysis as well, where we did some preliminary work that led to a company that's actually producing iron by electrolysis. And the whole concept there was that we realized that clean electrons are coming, or green electrons are coming. And the goal is then to try to take a look at all of these industries, these particularly metallurgical industries that produce their metals and materials using carbon. And so trying to develop processes to avoid that has been my sort of goal. I've worked in aluminum electrolysis going forward, and now looking at producing lithium using electrolysis and using it and producing it without using carbon as a reductant. So we have the choice of how do we address this issue of decarbonization, and the whole issue is trying to replace the use of carbon as a reductant. And we do that either by substitution. There was a lot of talk about using hydrogen, producing hydrogen, and then trying to make metals or other materials using hydrogen as a reductant, and the product being water vapor, which is nowhere near as harmful to the environment as CO2. Or do we just go right to making electrons and then using electrons to affect chemical change? So these are the sort of the things that I wanted to address in the panel today. Our panel today is focused on the R&D needs for industrial decarbonization through the use of electrochemical processing. And today we have 4 panelists with us. Laurel Harmon is the Vice President of Government Relations at LanzaTech. And Laurel, perhaps you can provide a few comments to introduce yourself.
Thank you. Is there an introductory slide there just for us to see? Great. So this has been a wonderful session. You've been hearing about innovative approaches to redesign manufacturing to reduce emissions. And LanzaTech's goal is actually to decarbonize industry right now by capturing the unavoidable carbon-rich emissions from existing operations, and to use those to make products that don't have a carbon-free alternative, like materials, clothing, beverage containers, and fuels for hard-to decarbonize sectors. Our core technology illustrated in the middle is gas fermentation. Like beer making, our biocatalyst lives on the carbon and energy contained in gases, which themselves can consist of carbon monoxide, carbon dioxide, and hydrogen. The process makes ethanol. It also makes other chemicals directly from industrial emissions. And it's a platform for a whole portfolio of products, as you see at the right, including what you might not think of, which is a nutritional byproduct. 2 plants are operating commercially in China today, making ethanol from both steel and ferroalloy emissions. And ArcelorMittal is in the late stages of building a plant in Europe with others starting up soon. So just to illustrate, products from our emission-derived ethanol have been announced by L'Oreal and Total, by Unilever, and by Mabel and Lululemon, just to give you a few examples. If you look at the upper left, you can see how electrochemistry is still very important to us, even though we're using biology, because low-cost green hydrogen, clean hydrogen, and CO from reduction of CO2 can be used to augment industrial off-gas, or it can be used themselves for full CO2 utilization into products. So look forward to the panel, and thank you very much.
Thank you, Laurel. We also have on our panel, Diju Lui, who is a senior chemist at Argonne National Laboratory. DJ, would you like to have some introductory remarks? DJ?
Sorry, I just unmuted myself. Good morning, everyone. My name is DJ Liu. I'm a senior chemist from Chemical Science Engineering Division of Argonne National Lab. My current research interests including green hydrogen production through water electrolysis, fuel cell, hydrogen storage, more recently, carbon capture and conversion. Some of my contact information is posted here in case you need to reach me. I'll be more than happy to discuss more with you. Before I joined Argonne, I worked at Honeywell International as a senior principal chemist. And I received my PhD degree from University of Chicago and I did a postdoc at UC Berkeley. So those are my background. Instead of discussing me, I would like to actually turn attention to some of the activity going on at Argonne, particularly in the domain of electrochemistry for decarbonization. Argonne is one of the few national labs have a very deep programs covering from basic science to applied science. And this actually created a very unique opportunity for us to address electrochemistry for decarbonization. To sum up some of the bullet points without going through detail, which will be too long, we have a material innovation, both in applied and the basic areas. We have a strong program in electrocatalysis research, membrane research, electrolyte, and electrode. We have device engineering, for example, electrolyzer, fuel cells. Of course, we have a really strong battery program in Argonne. Everybody knows that. We also have a program in deionization through capacity separation. On the process side, migrating from fundamental understanding to the application, we have a roll-to-roll manufacturing that can take over the development from device engineering to make it scale up and relevance at a prototype scale relevance to the industrial application. Of course, Argonne is known for its depth in analysis and characterization. We have a very strong artificial intelligence and machine learning program going on the basic side, as well as the techno-economic analysis and life cycle analysis on the applied side. We have a very strong facility to do a top level material characterization, including, for example, advanced photon salts, which providing a depth in synchrotron X-ray characterization work, as well as Argonne Leadership Computation Facility, which providing a large-scale computation to drive to support AL and ML activities. Of course, Argonne has also a pilot plant scale, the scale-up facilities such as the MERF and the camps you have heard about so far. I just want to touch upon a very brief topic that we're currently developing as a concept. This new topic is addressing the decarbonization process through what we call the CO2 refinery concept. We are currently developing a family of catalysts that can convert CO2 directly to chemicals, particularly with a strong emphasis on the C2+ chemicals. This will have an advantage to couple with the upcoming ample amount but intermittent renewable energy using both low and high temperature electrolysis technique to convert CO2 directly to, for example, ethanol, acetic acid, ethylene, or even methanol or formic acid. Some of this has already been demonstrated in our lab with fire efficiency over than 90%, which is really unprecedented based on some of the catalyst technology we're developing. So the advantage of this technology essentially create this a CO2 refinery that you can take the CO2 coming either from sequestration or from the pilot plant or from plant production and convert them directly to the chemicals on site. By changing different kind of catalysts, you can produce different chemicals. I should mention all these chemicals I mentioned are among top 70 most produced chemicals in the United States. So we could use this as a support the AMO's direction in terms of recycling CO2 and drive the chemical synthesis by using this approach. On the right side is some of the most, I mean, this is I couldn't possibly bring everybody's contribution science publication in this area, so I just listed a couple of patents that recently granted to Argonne, to my team, as well as some of the publications in this domain. So with that, I'll turn back to you, John.
Thanks, DJ. I'd like to introduce now another panelist that we have, Kate Peretti. She is the technology manager from the Advanced Manufacturing Office, U.S. Department of Energy. Kate, do you have some introductory remarks?
Sure, but I will keep it brief to make sure we have time for questions. My name is Kate Peretti. I'm a technology manager in the Advanced Manufacturing Office. I have put up on this slide the three main areas of activity that I participate on. So I manage the Rapid Institute, which was mentioned earlier in Joe's talk as being focused on sort of radically improving the energy efficiency of process industries. And that is really what they are focused on. They're focused on process intensification and modularization. And then I also work on the Bottle Consortium and other plastic upcycling technologies that are looking at basically taking plastic waste and converting that plastic waste to an intermediate that is able to be upcycled or recycled to a valued product to incentivize recycling and the circular economy for plastics. And then finally, I work very closely with Joe on industrial decarbonization, and we within AMO have sort of an emerging portfolio around industrial decarbonization, which I manage some of those projects as well. So you can see in this chart that was basically pulled directly from Joe's talk, that there's that wedge around industrial electrification, and that's been an area of interest for me. And so as part of trying to better flesh out the work that is needed in that area, I held a workshop back in June of this year to better understand the opportunity space and the R&D needs around industrial electrification, and specifically around electrochemistry for manufacturing. So with that, I guess I should also say that although it's not explicitly called out here in the bottle and rapid boxes, although you can see electrocatalysis in, if you really squint in the bottle box there. Electrochemistry is actually something that is a part of all of the work that I do, both in upcycling. There's components of it in rapid, and then also in the industrial decarbonization projects. So a little bit of a common thread. Thanks.
Thanks, Kate. And then finally, for our fourth panelist, we have today Brian Story. He is the Director of Accelerated Materials Design and Discovery Program at the Toyota Research Institute. So Brian, if you have some introductory remarks.
Sure. Hi, everyone. My name is Brian Story. I work with Toyota Research Institute, which is part of the Toyota family. We're a relatively young organization with a mission to develop technology for future mobility. So I work for the Energy and Materials Division. We have a mission to help accelerate the development of emissions-free mobility. So we have three thrusts: materials design and discovery, really focused on next generation materials for 2050. We have a strong thrust in battery manufacturing. Toyota is going to spend over $10 billion over the next several years building battery plants. They're trying to optimize and squeeze every dollar we can out of that extremely challenging business. And we also work on systems analysis around carbon neutrality and a pathway. So beyond technology, but the interaction of technology, economic, society, and policy, really to try to help decide, help with strategic decision making and things like that. So with that, let's jump to the questions.
Great. Thanks a lot, Brian. And as actually part of the questions, I wanted to follow up on something that Kate just mentioned a few minutes ago. Kate, you held an electrochemistry workshop in June, you mentioned. Could you comment on the key takeaways from that workshop?
Sure. Yeah, thanks, John. And I hope all of you attended. We had actually fantastic attendance all throughout the workshop, which was really great. And I think I'm going to echo a lot of what was said in the earlier panel. So it was a 4-session workshop series. So I'm going to try to distill it down to really some of the key takeaways. So, one was that, it was clear that one of the main motivations of pursuing electrochemistry for those in industry is decarbonization. They are starting to look at, how they can contribute to decarbonization in their, in their own manufacturing processes. And so that is a major motivator. That said, I think it was touched on several times in the earlier panel that in the absence of incentives, there's really no kind of financial force pushing towards electrochemistry at this time. So a lot of, although that's kind of the background incentive, those applications that are going to be successful are really going to have to bring along some co-benefits and or be really the only feasible solution for for these processes. So things like CO2 upgrading are really challenging to do in other ways. So that said, I think at a high level from an applications, we looked at what's the application space, what are kind of the key areas that people are looking at, and then also what are the associated R&D needs. Just a couple highlights. Obviously, CO2 conversion was one. Making chemicals to act as long-term energy storage was another key theme that came out. So, managing that intermittency, not only from an hour-to-hour perspective, but from a month-to-month and a longer-term storage potential. There were, we looked along 3 main lines. We looked at chemical manufacturing, metals manufacturing, and then water purification, because that's how it kind of synced up well with the AMO mission space. And so from more of a metals perspective, metal, critical material extraction, and also recycling. Recycling was a major theme that kind of carried through both metals and the chemicals areas. Obviously, generation of hydrogen as a renewable fuel and feedstock is a major thrust that I think Joe mentioned as well, that can contribute to decarbonization. And then just in general, there was a bit of a tension between those sort of maybe higher value products that might be produced at lower volumes, but that clearly demonstrate, value proposition for electrochemistry versus those major high volume, more commodity materials that might not have a high price, a high profit margin. And so may be harder to justify, R&D investment, but would have a much more significant impact from a decarbonization perspective. So, no clear answer there, just that tension was clear. And then from an RD&D needs perspective, I think if there was one theme I had to call out, which I think was also mentioned in the earlier panel, is scale up, scale up, scale up. There's a lot of work going on at the bench scale, a lot of really great innovations coming out of the national labs, including A&L. And we need to have the capability to then take those innovations and scale them, even to, as was mentioned in the earlier panel, to the demonstration scale. So, that goes along with, the materials, the cell components, and all of those things need to be able to be scaled. Standard protocols for testing and LCA analysis was another theme. So to the extent that there can be clear comparisons and kind of standards to follow would be helpful. And then also the materials challenges that I also think was mentioned earlier, around, again, scaling of materials, but also the durability, their tolerance to impurities, and resistance to fouling. All of those things also came up. So
great. Thank you so much, Kate. Laurel, sort of along the same lines to you, as a technology company that's involved in R&D, where do you see the greatest needs for electrochemistry for advancing the decarbonization of industry?
So for us, our technology itself is a biochemical process. It's a biological process. So where we're really keen to see electrochemical advances is in the front end, in producing low-cost hydrogen, in conversion of CO2 to CO, and allowing us to be able to access those feedstocks at low cost. When we're using industrial waste, those are low-cost feedstocks. The addition of hydrogen allows 100% utilization of the carbon and CO2 if it's present. Clearly downstream, there are already quite highly concentrated CO2 sources. The organism doesn't need carbon monoxide, but it does need hydrogen if it's only CO2, or that CO2 needs to be converted to CO to provide energy. And so our interest is really in having low cost and highly efficient upstream processes that we can couple to the gas fermentation. I have to echo in a general way that scale up is extraordinarily important. It's sometimes people who are more in the research phase as opposed to down in the demonstration and deployment, the last 2 Ds, don't necessarily have a vision of how long it takes. Our process did not exist anywhere in 2005 when our company was founded, and it took 13 years for the first commercial startup. And we don't have time for new technologies to follow that path, certainly any more slowly than we did, and we worked really hard at it. So investment in scale up, investment in demonstration, really understanding how any of these technologies can be brought to bear on decarbonization of industry is critical.
Great. Thanks a lot. Thanks a lot, Laurel. I have a question for Brian. As we're talking about the need for scale up, is there a role for AI in advanced computing technology in trying to define or push the frontiers of electrochemical materials development that can sort of accelerate the whole development cycle, get us to scale faster?
Yeah, so I mean, I think most people would agree new materials, especially for these long-term challenges, are really vital. And so being able to move faster, to iterate faster, design faster is a real critical capability. So acceleration is the goal. Towards that goal, AI is one tool of many that can, I think, help accelerate some processes, right? So depending on the job, it could be really useful. Sometimes it's not so useful, right? So it's one tool in the toolbox. I would say being data-driven is definitely a win. I don't think there's anything new about this idea. And I think in electrochemical systems, being data-driven is really critical because of the complexity of the problems, right? We lack good physical theories. We're limited in what we can compute. Reliable measurements, tracking what's been done is a real kind of critical thing. So having good data to build off of and make our decisions and design decisions, I think, key. And given the complexity of the problem, how else are we going to optimize other than through data? And so while this idea of automating experiments, generating a lot of data isn't new, I think the new question is whether AI can do a better job at somehow creating more knowledge from this data. Can we use AI to guide our experiments better? Can we use it to increase our speed of iteration? I think those are relevant questions. In answering them, sometimes AI is framed as this revolutionary thing, but if you look at successes, it's maybe a time to be a little humbler and more modest and see it as more evolutionary. Sometimes claims in machine learning are out there, but really when you look closely, it's more like what I would call statistics. Optimization might look more like classic design of experiments. So I see it as kind of a natural evolution of things that have been going on for a long time. I would say I'm relatively enthusiastic about the potential of autonomous systems that can discover things on their own, execute experiments, decide what to do next, form hypotheses, make predictions, and kind of run the cycle in an automated way. This is an old idea that's been around for a long time. There's a long history, but I would say we're getting better at solving real problems this way rather than toy problems. So, but all that, I would still sort of claim that even though it's exciting, there's still a very long road to sort of integrating those discoveries into devices that didn't scale. And so that's just going to always be a real challenge.
Right. Thanks, Brian. I have a question for DJ. I mean, in this whole industrial decarbonization R&D sector, as a national lab scientist, what do you see as the most exciting area of investigation, and why do you think that would be? DJ?
Thank you very much for that question. Actually, this is a really good question. Let me first and foremost to mention that electrochemistry applied in industry has already been in full swing. A case in point is, for example, the new battery technology are now implemented to the transportation sector and energy storage sector that had already made a major impact on the decarbonization. So when we talk about the next generation new technology, we should emphasize there's many new electrochemical technologies currently being implemented in industry. That being said, we're far from to reach the goal to the deep decarbonization. One thing that I think, as George already touched upon, is let's look at the fundamentals of the electrochemistry. Electrochemistry is dictated by gypsy-free energy, compared with a lot of conventional chemical processing or other industry processing that based on heat-driven process. One is gypsy-driven, which is dictated by the Carnot cycle. Therefore, electrochemistry obviously has potential to reach very high efficiency compared with the existing technology. That being said, it is really difficult to implement. It's not people do not understand this simple concept. People knows that, but it's simply because there's a lot of technology challenge. How to overcome that essentially is the point. I'm a physical chemist myself, so I work on the catalyst a lot. So I'm a little bit biased towards emphasize on the catalyst aspect. So the catalyst by itself is actually a science that you basically to rearrange molecule from the one you do not want to the one you want. To do that, your number one principle is this rearrange process has to be energetically feasible. That we all know, and that's easy to calculate. The most challenging one is how do you make it kinetically feasible? That's most of the catalyst people are working on. Those are the most difficult things from science aspect to drive the catalyst or the electrocatalysis into the application domain. One particular example that I'm particularly interested in right now is, I'll name two areas. One is, of course, I'm very interested in CO2 mitigation and conversion from CO2 to chemicals, and I'm actually working on this. One of the projects I support is funded by AMO to convert CO2 to ethanol. There is a lot more can be done in that domain based on essentially, literally the technology breakthrough from the catalyst side, that if you can generate a highly efficient catalyst, so substantially reduce your kinetic barrier, you can do a lot of things using the existing feedstock at low energy consumption to generate the chemicals that you want. Those are the things that I think we're going to continue to develop, and hopefully through the internal and external support to expand it, as I mentioned earlier, the CO2 refinery concept. Another nascent technology that's coming and everybody talk about is ammonia production using a green hydrogen or using a direct ammonia electrochemical process converting nitrogen to ammonia. That is a really exciting technology field. And if that can be successfully launched, that can be substantially reduce the CO2 emission and improve energy efficiency. So I can only providing a very small sliver of what I think is important in terms of electrochemistry to the current technology development.
Right, thanks, DJ. I just have one more comment to make. Just as we go forward to try to address some of these key R&D needs that we talked about today, is there, how can industry and small business and government and academia, how can we all organize better to help accelerate this whole area to advance the decarbonization through electrochemistry? What kind of organizational structures do we need to go forward? I mean, that's open for all of you. Anybody would like to start?
Well, maybe I can start. I think this is a time when we do need all of those different groups, like national labs, in academia, industry, both small and large, and government to work together to solve these problems. One of the key elements that we have found in those collaborations has been very early engagement of industry. Whether or not industry partners such as ourselves or other industry partners are performing R&D at the earliest stages, our involvement in advising on requirements, on looking at economic potential and market potential, provides early information that can guide R&D towards something that will have a real impact in the world and be able to be scaled up. The government has a wonderful and proven role in convening collaborations between labs and universities and industry. We ourselves have had a number of successful collaborations of that type, including work with almost all of the national labs. One example is the development of something that only remotely looks like it relates to industrial decarbonization, but the development of sustainable aviation fuel technology using ethanol feedstocks. And that is actually, it originated at PNNL. We worked on it together for about 9 years with support from Vito and other industry partners. And that's being commercialized today. And the link is that Virgin Atlantic actually flew on ethanol made from steel mill emissions that was used to produce sustainable aviation fuel. And that was used in commercial flight in 2018. So that's just one example, but there are many, and it's a really rich time. And I think in particular, government catalyzes collaborations at a stage that they would never take place otherwise.
Thanks, Laurel, for that. Others can comment on that?
I'll just add something. So, I mean, the future is uncertain. Nature's solution to uncertainty is diversity, like try everything and see what works. So I think having everybody involved, trying lots of things is great. If I had a good answer to your question, we'd be doing it. I think it's a really, really hard thing. So, if I think of something that's maybe a little simpler, more achievable, maybe that could be really important, is something Kate kind of touched on in her at the beginning, is really around metrics and kind of agreement on what are we really trying to do here, and how are we going to compare these different technologies, and what are the real bottlenecks, and what are the key performance metrics, and how do we evaluate whether we're really making an impact with all these different technologies. And you look at a lot of these things and you can find answers that vary by orders of magnitude. So real clarity on how we're going to assess these different technologies and whether we're doing something. If we could agree on that as a community, that could be, I think, a big win, and seems maybe somewhat achievable anyway.
Thanks, Brian.
If I may add some in this particular topic, and here's what my 2 cents are. I think going back to my research career, I do realize there's an important aspect of all this technology that we're developing going forward, hopefully it will change our lives, is we could not basically neglect the importance of a basic science to lead the technology development. I participated in a couple of programs in the past, and people were trying to essentially push the technology forward without sufficient basic science report. It turns out always are not very successful in those domains. So to lead the process through basic science is critical in the upcoming decarbonization, electrochemistry research, or any related research. That being said, I think being working in industry before, I do notice there's a major culture difference between academia, national lab versus industry. That culture sharing should be as an important factor going forward in terms of structuring new program. Case in point, when I work in industry, we have problems that need to be addressed, as Laura already mentioned. Those problems probably have a time life for anywhere from 3 months to 2 years, and you have to address them. Otherwise, you can either solve them or you move on. You do not hang on this forever, because this is just not going to be feasible. Yeah, I think the university and the national labs could borrow that culture and trying to accelerate the pace to commercialization from their science.
Great, thanks, DJ. Kate, I'll give you the last word on this.
Great, yeah, and I'm so pleased to see Brian and Laurel jump in first, because I didn't mention this explicitly, but so both the Bottle Consortium and the Rapid Institute are public-private partnerships, right? And so I am part of the consortium team, which means I am a firm believer of bringing together people from industry, academia, national labs, nonprofits, and anyone who can contribute to the solution of these problems. And that is what those public-private partnerships are really established to do, is to bring these folks together to accelerate the development and deployment. And we really believe that, as Laurel mentioned, bringing in industry as early as we can to get their input and help guide some of this work is really critical to that accelerating towards deployment. And to DJ's point about, everything has to be on solid, basic science foundation. There are a lot of basic science problems, even at higher scales, more towards deployment. And so I think, yes, and yes, I think, we need all of those things. And I believe that, whether bringing folks together on, large project teams, which we do through R&D projects, or bringing folks together through consortia, I do think that teaming approach is really the most effective method to accelerate advancement.
Great. Thank you so much, Kate. And I want to thank all the panelists for a very interesting discussion today on the R&D needs for electrochemistry. Well, sorry, the R&D needs required for industrial carbonization using electrochemistry. So thank you all. Thank you, Brian, DJ, Laurel, and Kate. Thank you all very much. I'm going to turn it over now to George to continue our webinar.
Wonderful panel, John, and panelists. Thank you so much. I fully agree. You've pointed out how broad in scope this challenge is, going all the way from basic science to actually deployment of technologies, and it's a real opportunity. Our next speaker is Megan Clifford. She's Argonne's Associate Laboratory Director for Science and Technology Partnerships and Outreach. And she will tell us a little bit about how to cooperate with how to work with Argonne. She focuses on maximizing the outcomes of existing collaborations and partnerships, supporting the creation of new collaborations and partnerships, and fostering lab-wide strategy and program development, all with the goal of increasing the impact of Argonne's work. So before taking this role, Megan served as Argonne's Chief of Staff. She has a BA in International Business from the George Washington University and an MBA from Northwestern's Kellogg School of Management. So really pleased to welcome Megan. And Megan, the floor is yours.
Great. Thank you, George. And good afternoon, everyone. I'm Megan Clifford, Argonne's Associate Laboratory Director for Science and Technology Partnerships and Outreach. It's really my pleasure to be here with you today. And I found the discussion with that panel just really fascinating, highlighting the R&D needs that we need as a country. And I'm excited for what's up next, which is the Argonne tours. So make sure you stay online for those virtual tours. With that in mind, I'd like to talk just a bit about Argonne's collaborations with industry and academia and our approach to technology transfer and partnerships. Argonne has a long and proud history of engaging in partnerships that enable pivotal discoveries, advance promising technologies, and deliver value for our partners. These partnerships typically come in one of three forms. First is collaborative R&D, which is generally cost shared. Second is R&D conducted solely by Argonne for a partner, and it is sponsored by that partner. And finally, organizations can purchase the rights to Argonne inventions for the purpose of commercialization. In the case of decarbonizing industry through electrochemical processing, Argonne is currently engaged in multiple efforts with industry and academic partners. One example involves Argonne, Northern Illinois University, the University of North Texas, and Angstrom Advanced Incorporated, a company in Massachusetts that designs and manufactures hydrogen electrolyzers. The Department of Energy is funding the 3-year project to develop a prototype low-cost system for capturing carbon dioxide waste from manufacturing emissions and converting it into ethanol. This project is an outgrowth of the discovery by Argonne and Northern Illinois scientists of a new electrocatalyst that converts CO2 and water into ethanol with very high energy efficiency and high selectivity for the desired final product. Another example is a partnership between Argonne and Javo Inc., a Colorado-based company that produces energy-dense liquid hydrocarbons, such as sustainable aviation fuel and renewable premium gasoline. In this partnership, Argonne and Javo are performing a critical life cycle analysis of Javo's next generation technologies. Using data provided by Javo, Argonne is applying its world-renowned GREET model to deliver results resulting in insights into carbon footprints of these fuels. This effort is also being funded by the Department of Energy. Those are just a few examples of the types of mutually beneficial partners in which we engage. From the Department of Energy and Argonne's perspective, it's really part of our mission to ensure that US companies have access to our cutting-edge expertise, facilities, tools, and IP. For US companies, this type of collaboration opens new doors and helps to better compete in global industries. If you're interested in exploring how your organization, large or small, might collaborate with us to overcome technical hurdles or capture opportunities in the market, we have a team of experts to help you consider what's possible and what might make most sense for you. These are professionals who have both the technical know-how and business acumen, so they are well equipped to assist you. A good first step is to contact manufacturing at anl.gov so Argonne staff can connect you with the right people or groups to facilitate a conversation. If you decide to work with Argonne, a member of my team will remain engaged with you throughout all stages of the collaboration lifecycle. So thank you for the opportunity to be part of today's event, to learn more about the different organizations and people's needs, goals, and perspectives. At Argonne, we really witness every day how collaboration unlocks innovation. And that certainly applies to our work with industry, universities, and other partners. So thank you again. And with that, I'll turn it back over to George. George, please.
Thank you, Megan. Really appreciate your contribution and your telling us how to work with Argonne. That can be a very important step forward. We'll now turn to our three tours. We have three guides and three stops. First, we'll meet Justin Connell. He's a materials scientist and manager of the Electrochemical Discovery Lab. He'll give us a tour of the lab, show us how the scientists use this facility to research electrochemical processes. Next, we'll hear from Chris Pupek. He's the group leader for process R&D and scale up. Chris will give us a tour of the Continuous Flow Reactor Lab. That's part of MERF. He'll show us how the lab fits into his work on scaling materials and technologies up to commercial levels. Finally, we'll meet with Meltem Ergen-Demertis, who leads the Bioprocesses and Reactive Separations Group. She will guide us through the Electrodialysis Pilot Plant, where she and her colleagues research large-scale electrochemical manufacturing processes. So let's start now with Justin in the Electrochemical Discovery Lab. Justin?
Hey, George. Hi, everyone. Thank you for the introduction. As George mentioned, my name is Justin Connell. Am I good?
Yeah, we can hear you.
Oh, you can hear me? Okay.
We can't see you yet, though.
Okay, we're getting the camera sorted out. Are we good?
There we go. You're on now.
All right, great. All right, so yeah, thanks for the introduction. As George mentioned, my name is Justin Connell. I'm a materials scientist here at Argonne and manager of the Electrochemical Discovery Laboratory, or EDL as we call it. And right now we're standing in one of several labs that make up the facility. The EDL was established by the Joint Center for Energy Storage Research, or JCESR, which is the energy innovation hub that's centered here at Argonne, but is it a collaborative organization that's spread across multiple national labs, university and industrial partners across the country. And our goal in JCESR is to look at next generation battery technologies that move beyond current lithium-ion systems. Now we're an interfacial electrochemistry lab, and what that means is, all the action in an electrochemical system happens at the interface between your active electrode and the electrolyte transporting ions back and forth. And what we want to understand at atomic and molecular levels is what are the key processes that guide those interfacial reactions that dictate the electrochemical process you're trying to drive. While that sounds really basic, and it is very fundamental research we do here, it's always with an eye towards the applied. As I mentioned at JCESR, we're trying to develop new battery technologies. And so we've really developed an innovative approach in our lab and world-leading facilities to go after these questions. And these facilities and approaches have really allowed us to work not just on next generation technologies, but with more applied offices in the DOE, such as Energy Efficiency and Renewable Energy, VTO, Vehicle Technologies Office on solid state battery systems, as well as with vehicle companies like BMW on more traditional lithium-ion systems, as well as industrial consortia on things like lead acid batteries. And as I mentioned, what really lets us look at these, broad spanning of different TRLs is our unique facilities and unique approach to looking at electrochemical problems. So behind me is sort of where some of this process starts. So directly behind me is a tool for putting down thin films of electrode materials. So we want to make very well characterized electrode materials. So we can put down thin films of any kind of material we like, metals, metal oxides, complex metal oxides, which are the starting point for the electrochemical reactions we want to study. We can then take these materials that we've made in this tool and move over to this other system right here, which is an interfacial chemistry analysis tool. Basically lets us use different types of spectroscopy and structural analyses to understand what is the chemistry and surface structure of the materials that we've made. Once we have that handle on sort of what, that we have a high degree of confidence that what we tried to make is actually what we wanted to make, we can then take these materials from this analysis module and move it down this long transfer line. So we can move between synthesis, characterization, and then through this transfer line down into a controlled atmosphere glove box to then go and do the electrochemistry, the actual action with the materials that we have synthesized in this lab. And you notice there's a lot of empty space on this, and I'll come back to why that is in a minute, but this was an intentional design choice on this specific system. Now, of course, we want to have information not only just on the electrode materials we're working with, but also the electrolytes that we're using to drive the electrochemistry. And so some other labs throughout the facility, we have capabilities for synthesizing and importantly purifying and then characterizing the electrolytes that we work with, so that we know with a high degree of fidelity, what is the purity of the materials we're working with, what are the critical residual species that we have left over, so that we know when we start to go and do electrochemistry, what exactly we have in our system from the beginning. Now, of course, we want to actually do work with these materials, not just make them and understand them. So we have also significant facilities within the lab that allow us to then look at these materials as we cycle them. So we can do in situ spectroscopy to understand as we cycle the materials, how do they degrade, what kinds of species are formed on the surfaces of the electrode materials, and what the composition of those layers are. We also have the ability to monitor how these the materials themselves break down, the electrode materials. We can look at corrosion in situ as we cycle the battery or the given electrochemical system. And then finally, we have capabilities to look at gas evolution. So if we're working, either driving a process where gas is intentionally involved or where gas is an unintended byproduct of some heat composition reaction, we can understand how those materials are breaking down, what are the products, and importantly, what concentrations and efficiencies are being formed with. So now once we've done all this analysis, we've made our materials, worked with our well-qualified electrolytes, and then cycled them under some kind of protocol, we can then take those materials directly from the environment that they were cycled in and bring them back through this analysis tool, back over to our surface spectroscopy tool and understand how have they changed as we've done cycling? What does the chemistry of the surface look like? Has the structure of the material changed? Have we done some kind of unintended reaction? Is there some kind of film that's formed on the surface? We can understand from essentially the cradle to the grave, how the materials have been made, synthesized, or have performed, and then how they've broken down with time. And the key to this whole process, and why we go through all this trouble, is because what we ultimately want to do is learn how to fail fast. We want to understand, what are the critical components of materials and the electrolytes that drive performance? What are the critical impurities that we have to control? Because at the end of the day, the systems that we're making are things that we want to be able to scale up. We don't want to just understand, but we want to use this understanding as inputs to then scaling these technologies, to making new materials that perform better with structures that we intentionally want to develop into them. And so, I've talked a lot about, this in terms of battery systems, but really the approach that we use in this lab is relevant to any electrochemical system. Again, interfaces are what drive electrochemical processes, and we're set up to do the deep science necessary to understand those interfacial processes. And then say, what are, again, the key impurities, the key species that we have to control, so that when we hand these technologies off to somewhere like the materials engineering research facility, they know in their scale-up activities, do we have to really control water content? Or is there another, critical impurity that we have to control here? And critically, we put a lot of effort into developing world-leading capabilities here, but we're also built for expansion. So I pointed out this long tube behind me that has a lot of space on it. And that was an intentional design choice in this lab. So that as we move into different technology areas, looking at different problems, we have the ability to expand, to bring online different characterization tools, different imaging capabilities, different synthesis capabilities, so that we can work with the materials as the problems arise that we need to understand what are the critical components to failure. At the end of the day, as I mentioned at the beginning, interfaces are key to any electrochemical system. And so we really want to be able to understand in this lab how we can control those interfaces and how we can make materials and electrolytes to ultimately make very well high performing systems. So with that, I'll turn it back to you, George, for any questions the audience may have.
Justin, thanks so much. We do have time for probably one question. Is there a question that someone would like to ask? And either through Q&A or if it's someone available in the mic, just speak up. I'm curious, actually, Justin, what are some of the things that the laboratory has done? Can you point to one or two things that have really had an impact in the battery space?
Yeah, so I'd say one I'd point to is sort of the development of new design principles for electrolyte development. So one thing we do a lot of in the battery space is try to design new salts for performance, or come up with new additives. And what we really understood in this lab and been able to figure out is that there are actually design principles that span multiple chemistries, not just the specific one like a magnesium ion or a zinc ion system, but actually across all chemistries that can be used to generally design new salts, new electrolytes for these systems. And so we're really pushing the boundaries of kind of what can be done while taking the burden off of some of the electrolyte design folks. We don't have to create one salt that does all the work. We can actually leverage multiple constituents that will actually allow us to get a better performing system than we might out of the single systems themselves.
Great answer. Thanks so much, Justin, for that explanation of the EDL. It's really an impressive facility. Let's turn now to Chris Pupek in the Continuous Flow Lab. And Chris has a pre-recorded video that he's going to show us, and then he will be here in person for questions. So can we start that video?
Hello, and welcome to Materials Engineering Research Facility, MERF for short. My name is Chris Pupek, and I am material chemist. What are we doing over here at MERF is called Process Research and Development. Why we needed process R&D, and what is it? So the discovery scientists, when they create new material in the discovery lab, they make it in the very small scale, which is sufficient for the basic investigation, but for the prototyping and full-scale industrial validation, there is a much larger quantities needed. And the objective of the discovery scientists is to create the material as quickly as possible. So they use techniques that is very efficient in the very small scale in the bench, but cannot be directly used for producing of the larger quantity of this material. This is why we need process R&D. The objective is to develop optimized process. Optimized and efficient process means lower the cost of manufacturing without compromise quality and performance of the material. So here at MERF, we investigate and apply emerging technologies, how to make the material more efficient way, using domestic feedstock materials, develop the process that use less energy and generate less waste. One of the technology platform we use in this particular lab is called Continuous Flow Chemistry. In the typical manufacturing of fine chemicals, the industry employ so-called batch process. Means that all the chemicals are put in the reaction vessel. There are heat, chill, stir, whatever is needed. When the process is complete, the reaction is drained to recover the material clean, and the process start over. That's the batch. In the continuous flow, the technology is completely different. We have 4 different commercial continuous flow reactor, each of them with different capability and purpose. One of them I want to show you is the Argonne continuous flow reactor. So the main difference between the batch and continuous flow is that in the continuous flow, the reagents are actually stored outside of the reaction vessel. The reagents are on site, and through the system of pumps that are constantly pumped through the reaction vessel. The actual reaction vessel is the array of these microfluidic chips. And the product is collected constantly outside. There is a lot of benefits of continuous flow versus batch reactors. We don't have really time to discuss all these technical details, but safety of the process, the hazard associated with the chemical process can be directly translated into the cost of the process. Because in the each given time, only very small amount of these reactive chemicals are in the reactor, the hazard is mitigated. Another benefit is that usually in the continuous flow, the reaction is much, much quicker, means save time, save money, is very clean, means less waste is generated. And this particular reactor is very good for heterophase reactions. When one of the reagents is a liquid, one of the reagents is a gas, for example. Another continuous flow reactor system we have is this one. This is for the slightly larger scale. What is unique about this particular instrument are the plates that are made out of silicon carbide. Silicon carbide has a very good resistance to harsh conditions and chemicals. When we need to use very harsh conditions or very harsh chemicals, we use silicon carbide microfluidic plates. Another one is the modular Asia system. As you can see, this consists of several different modules, each of them for a different purpose, including one module for electrochemical transformation of chemicals. This particular instrument is coupled with online infrared spectroscopy, so we can see in the real time what is the progress of the reaction and how much product, how pure product is produced. This is our new system. The whole bench is a one system, and the continuous flow reactor, which is this part, is coupled with analytical instrument. This is magnetic resonance, and this is a high-performance liquid chromatography. So the reaction product from the continuous flow reactor goes straight to the analytical instrument in the real time. The initial process parameters from the continuous flow reactor and results of the analytical instruments are fed into the artificial intelligence module, machine learning module that analyze and based on the results propose new set of parameters that is feedback to the continuous flow reactor. And this is the loop that allows for self-driving or so-called autonomous discovery lab. Very efficient way without any interaction from the scientists. We can very quickly develop optimum process parameters. And in our case, our machine learning module uses the algorithm that can optimize the process based on several different factors. So we are not only looking on the yield, how much of the desired material is produced, but for example, of the cost of reagents, impurity profile, and so on. So we can program the machine learning module to pick the best balance for specific material and specific application. We are working with other national labs, we are working with academia, and we are working with the industry. We are open for collaboration. We want to put the science to work to help the industry be in the forefront of advanced material manufacturing. So thank you very much for visiting Materials Engineering Research Facility Continuous Flow Reactor Labs.
So thank you, Chris. A wonderful introduction to what the MERF can do. It's impressive, I think, that there are so many different functions that you are looking at. We do have time, Chris, I can see you live now. We do have time for a couple of questions. We'll watch the Q&A and maybe Aaron, you could relay those Q&A questions that may come up. But let me ask you first, the machine learning is the very latest technique for both discovery and scale up how long has the MERF been working with the machine learning techniques?
Actually, this project was found by internal source. It's a part of LDRD, and we work on this particular system using a continuous flow chemistry platform coupled with machine learning and online analytical tools in the past, I would say, half a year.
So that's amazing. And what kinds of problems have you applied that to? I mean, you were mentioning one or two. I find it really fascinating.
Yeah, that's basically is our tool for the very fast process optimization. Imagine you have a reaction, chemical reaction. They have let's say 5 different parameters like a temperature, pressure, ratio of reagent, and so on and so on. If you start multiply all these parameters 5 times 5 times 5 and so on, it will give you thousands and thousands possibilities. So using the brute force to find the optimum process parameters, you will have to run all this experiment, analyze one by one, and somebody need to decide what we really want. Machine learning, this intelligence approach will basically streamline everything, and typically we can find the optimum process parameters within, let's say, 1 week. It depends on the complexity of the process and how many different parameters we want to investigate.
That's fantastic. Thank you so much, Chris. Really appreciate your time and all the information you've given us. Let's turn now to our final stop. That's with Molten Ergen-Demertis, who is in the Electrodialysis Pilot Plant. And she also has a pre-recorded video. So if we can start that video, that would be great. And thank you, Chris.
Decarbonization of industry and manufacturing sector. Electrochemistry-based technologies is crucial, and they are getting attention because of the decreasing cost of electricity. At Argonne, we have been developing many electrochemistry-based technologies, but today I would like to focus on 2 technologies. One of them is electrodialysis, in short ED, and also I would like to focus on electrodeionization technology. We have about 40 patents in last 20 years. Electrodeionization technology is an advanced technology which combines advantages of ion exchange and also electrodialysis. It composed of 2 ion exchange resins. Cation exchange resins allow only transportation of cations, and anion exchange resins allow only transportation of anions. And each ion exchange membranes are configured in a way that one ion exchange, and there's a spacer, and then for diluent, and cation exchange, and then there is another tracer for the concentrate, as well as all those stacks are covered by using the electrodes, cathodes and electrodes, the cathodes and anodes. When we apply the current to the system, electric current passes through the stacks in ionic form. So cations migrated to the cathodes and anions migrated to the anodes to conduct the selective transport. So when we look at the active sites of the membrane area, it is ranging between 1 centimeter square to 1 meter square, depending on the application size at each membrane unit. And also when we look at the spacers, their thickness has been ranging between 300 microns to the 2 millimeters. And the flow velocity is between 1 to 10 centimeters per second. In some cases, we increase the flow velocity up to 50 centimeters per second to overcome the poor mixing. The flow regimes at most of cases is steady state, but when we increase the velocities, it can cause turbulences. So we need to, in that case, regulate the pressure at the system. At industrial scale, EDI and ED is mainly used for desalination of brackish water for drinking water production, as well as we have been using these units for recovery of table salt from desalination of seawater, and also demineralization of cheese whey that is going to be used for baby formula. Depending on cost of electricity, EDI may be cost effective because they are less prone to falling, as well as they provide high flux and selectivity, which are very important parameters when it comes to the separation of any technique. And also EDI and ED units, they don't require much chemicals, or they never require any additional chemicals depending on the applications. At Argonne, we have been developing technologies for water treatment, as well as energy and chemical production, as well as for recovery of chemicals, high-value chemicals, and removal of toxins. For each experiments or for each development technologies, we start with the baby mini stack, as you can see here. We have been using resins as well as adsorbents developed at Argonne for the configuration of this EDI mini stack. And we conduct bench scale tests by changing the operating conditions to understand the performance of these new materials. Then we scale up the technologies to large stacks, or sometimes we also use manufactured stacks that we purchased from the vendors. Depending on the results, we scale up further the process. At Argonne, we have also a pilot unit, as it can be seen here, which has 1,000 gallons of water treatment capacity per day. Unfortunately, our EDI stack, which used to be here, is shipped out to California to be used for field scale testing. It is a highly instrumented unit and consists of many tanks as well as pumps for the treatment of wastewater. And also, I would like to take you to our plant unit. We have an EDI plant unit at Argonne, which has a capacity of 10,000 gallons of chemical production per day. And the tank, as I am pointing out, has a 10,000 gallon capacity to hold the product. And the next tank has a 10,000 gallon of storage capacity to feed the system, to feed the system with the influent. It consists of 8 tanks, and the other tanks have been used for preparation of electrolyte rinse solution, as well as acid solution and also base solution. I would like to also take our membrane that is used in the plant. We produce about 1.6 million gallons of chemicals over the 19 years. So to run the one batch of unit, we have to run the entire unit at least 18 hours per day. So I would like to take you to the heart of the plant, which is the stack. It is made of bipolar and ion exchange. It has about 1 meter square active membrane area, and it is made of many stacks. As you can see, it is made of three big stacks. So when the solutions pump through the system, we start the operations and we apply about 230 volt DC. And then after electrical potential applied to the system, reaction starts, and our operating resistance is about 160 ampere in DC. And within 18 hours, we will be able to produce about 10,000 gallons of chemicals. In summary, at Argonne, we have been developing technologies and scaling up them from bench to pilot scale and also full-scale plants. With that, I would like to conclude the tour. Thank you so much for your time.
Meltem, thank you enormously for that wonderful tour. We're running a bit short of time, so I think we'll skip the Q&A. But I do want to thank all our participants who participated, and also the folks who joined the webinar. Thank you. We appreciate your engagement. Hope this event was informative. And we look forward to seeing you in the future. Please remember that if you have any questions or feedback for us, please explore the potential for, or to explore the potential for a collaboration, please reach out to manufacturing@anl.gov. And if you would, please look out for announcements of future webinars in the Frontiers in Materials Manufacturing series. Thank you again for joining us today, and this concludes our webinar.